official contract before the 2 days of before the 2 weeks of projects. So we're very happy this morning to have Luca. Luca was educated in Rome, then took a variety of positions, well, a bit around the world, in the US and Europe.
And even close to here in Nice, at the Observatory of Nice.
Also in Nice,
yes.
Absolutely. And so you're back to Rome after a stay in Paris. And well, Luca is a very well-known expert in turbulence and has recently moved to machine learning. How can machine learning help you with understanding turbulent flows?
Yeah.
So thank you very much.
Okay, thank you, Guillaume. Thank you for the invitation. First of all, well, welcome. Good morning to everybody. Let me apologize that I could arrive only today, but I mean, I had a commitment in Rome that I could not escape until a few days ago. So it's a pleasure for me to be here and to have the opportunity to present our work and our point of view. When I say our, I mean the work done by my group in Rome that is at the moment composed by Tianyi Li, a postdoc with us from China, Chiara Calavascebetta, who is a PhD student, Michele Buzzicotti, who is a researcher, Robin Einonen, that is who is also here, I guess, somewhere. I don't see now. Okay, there, hi, Robin, who is also a postdoc in the group, and Damiano Capocci is a PhD student, and Fabio Bonacorso, who is our software engineer. What I'm going to tell, as Guillermo was saying, we have a background in turbulence mainly, and in complex flows, also at micro and nano scales. And since 2 or 3 years ago, we started to work to see if and how data-driven tools might indeed be helpful for our community. So I understand that my background is not completely overlapping with plasma physics and your community, but still I think there are many points that are in common. And in particular, in my presentation today, I will mainly focus on tools more than on applications, and therefore, I mean, tools are, of course, by definition, multidisciplinary. So our question, I mean, we started to work on this. The idea is to understand how much these tools that exist in the data-driven community since many years ago are indeed able to help us not only from a proof of concepts point of view, but also from a quantitative point of view, and how much they can really become, or if they already are, tools that can be exploited for frontier research whenever we have to do with complex fluids or complex flows. And let me also add that, of course, I mean, the work that I'm going to tell and to present you, the results that I'm going to present you, are not only made by the contribution of the people in the local group in Rome, but also by thanks to the collaboration with many other friends and colleagues that I've listed. I mean, the most recent ones I've listed down here. So well, first, the second part, second important point is, I mean, I would be very glad if you can interrupt. I mean, do not wait to ask questions at the end of the talk. We have plenty of time, so it would be good to have a sort of continuous interactions. Now, I don't know why it does not go. Oops, sorry. Okay. So whenever, let me give me the 10 minutes to position whenever I speak about complex fluids and complex flows. What do I mean? I mean, we are physicists from origin, so we tend to nevertheless try to simplify as much as possible the problem without putting too much dirty under the carpet. And so the typical setup that we are interested to control is a setup where, okay, this is very general, right? Where we have the Navier-Stokes equations, eventually the transport of some active quantities could be a scalar like temperature, could be a vector like the magnetic field, and these quantities might be passive or active. That is, in presence of gravity, you might have, for instance, a buoyant contribution in the evolution of the of the velocity field, or if the magnetic field is strong enough, you might have a feedback because of the Lorentz force. And most of the time you work in the incompressible case, even though, I mean, in principle, I mean, at least for the applications that I'm going to tell you today, there is no really restriction or any problem in trying to apply them to compressible fluids. And then in general, you know, you must, to fix the problem, you need also to fix the boundary conditions and eventually the initial conditions if you are interested to transient problems, and the external forcing. So I would say almost for the entire talk, I will try to simplify as much as possible the boundary conditions and the external forcing. So if not explicitly stated, for instance, when I'm going to speak about Rayleigh Bernard, I will always discuss problems where boundary conditions are periodic. I mean, I will try to avoid for the moment problems connected to the presence of the wall, even though, again, the tools that I'm going to tell you are not necessarily restricted to cases where you have periodic boundary conditions. And also the forcing, well, the forcing will depend on the kind of flow that we want to discuss. Another important point that I will try to discuss, at least later on, maybe this morning or in the afternoon, in the discussion that is planned in the afternoon, is not only the Eulerian description of the flow, and of the fluid, but also eventually problems connected to Lagrangian evolutions. And therefore, what happens whenever you also have a second phase, could be particles, could be small particles, could be the formable droplets or bubbles. I mean, depends on the applications. And you also want to understand the coupling between, first of all, the advection of the particles by the flow. If the particles have a different density of the underlying fluid, there is some inertia, so they are preferentially concentrated on different regions, and therefore even their global advection is not trivially homogeneous in the flow, and also eventually one could be interested, exactly like for the temperature and for the magnetic field case, to a potential feedback of the particles on the flow in all cases where the mass, the volume fraction is important. So I will try to present a few problems connected to both descriptions, the Eulerian description or the Lagrangian description, and in particular connected to tools that are based on data-driven approaches. One of our obsession is that whenever we present and we discuss data-driven approaches, we always wanted to compare with physics-informed baselines. I think this is really mandatory in order to make a step forward in the research. That is not only to show how much the tool based on data is performing, but how much we improve with respect to other tools that are physics-informed. Just to give you an idea of what are the typical questions that we are interested in the setup that I written before. Well, first of all, I didn't say, but I think it's almost clear by definition that I will be mainly interested in turbulent cases. That is when the steering mechanism is so strong, overwhelming dissipation, therefore where we have a huge range of scales where the flow is evolving in a chaotic way, both in space and in time. So in the turbulent regime, the kind of question that we are interested as theoretical physicists can be mainly summarized by these 3 points. Well, the first, which are, I think, all of the 3 strongly connected to problems whenever we want to use data-driven tools to study and to understand the physics of the flow. The first point is that, as you know, whenever turbulence is fully developed, we have power laws. And therefore, if you look at the energy spectrum, it is typically, I mean, if the flow is almost homogeneous and isotropic, you have the famous minus 5/3 slope. And the presence of power laws tell us that we cannot compress too much the number of degrees of freedom, that there is not a typical length scale unless you look at very small scales, very high wave numbers where there is the viscous dissipation. There is a huge range of scales where you don't have any typical length scales, which means that the attractor is highly dimensional and that there is very little hope from first principle to be able to compress the dynamics on a much smaller attractor. Right? So typically, if you have 2 or 3 decades of a power law in 3 dimensions, means that you have at least 10 to the 9 degrees of freedom that are active in your field. So the first problem is that, which is strongly connected to this data-driven approach, that are typically benchmarked on small dimensional dynamical systems, is that here we are dealing with problems where there are billions of degrees of freedom that are not compressible by first principles, because we know that they are active. The second point is that, as it's well known, let me just summarize, nevertheless, that if you go and you look in the real space, in the configurational space, what a power law like this means, then you immediately realize that you make a Fourier transform and you see that the typical velocity increments at a given distance r on your real space goes like r to 1/3, almost. So the 5/3 means r to 1/3, which tells you that in this huge range of scales, you have the velocity field, you have your fields that are not differentiables. And they have all the exponents order 1/3, and which means that any tool that is trying to interpolate or refill or repaint eventually damaged by using linear interpolation or even non-linear, but I mean analytical and smooth interpolation, it might be they are deemed to fail. So the roughness of the velocity field is another big problem for the data-driven approach, because data-driven most of the time are based on the idea that your underlying physics or structure is smooth and differential. The third point is that indeed the story is not ended with this exponent 1/3. So it's not that the flow is not completely self-similar, because if you look at the probability distribution function of the velocity increments as a function of the distance where you measure the velocity increments, and you fix the distance in this range of scales where we have power laws, you see that the PDF of these velocity increments, even if you normalize with the root mean square, the PDFs change by changing the reference scale. Which means that it's easy to see and to realize that it means that the exponent is not always homogeneously equal to 1/3. So there are fluctuations in this exponent of 1/3. That's why people speak about the multifractal statistics. But put aside the names and definitions, this is very important because it's telling you that even if you control exactly the physics at some distance, and the physics it's not enough to know how the root mean square is behaving by changing the scale to predict what is the PDF at the other distance. And what is very important is that you see by changing R, by decreasing R, the PDF becomes more and more non-Gaussian. And it's remarkable to notice that the degree of non-Gaussianity is extreme, in the sense that, for instance, at scales that are close to the end of the inertial range, you may have fluctuations that are 40, 50 times the standard deviation. So this, I mean, turbulence from that point of view is probably the wildest phenomenon we have in classical physics. There are no other real cases that I know where it's easy to measure fluctuations up to 60 standard deviations with a probability that is not so small, you see, of the order of 10 to minus 7, 10 to minus 6. And this is another big problem for data, not only for data-driven, but for everybody, for all approaches, because it tells us that we have extreme events. The probability to have extreme events is not so small, and that these extreme events are particularly are typical of the small scale properties of the flow. So it means that not only you have extreme events, but also you need extreme accuracy to measure, if you are an experimentalist, or to resolve, if you are a numerical people, the evolution of the flow. So the combination of these three problems indeed makes okay. I promised you that I would have also yes.
Just on that last block, if here you are in a case which is extremely turbulent with an enormous amount of intermittency and error. If you were to increase resolution, up to absolutely crazy resolutions, which is at some point stopped.
Okay, there are two different questions. You can fix Reynolds number and just increasing the resolution of your numerical code if you are numerical people, and then you know that if the scales these is inside the viscous scale, this would stop, and you would not see any change in the intermittency. On the other hand, if you increase Reynolds, right, so you have inertial range that is more and more extended, and therefore you can go to scales that are smaller and smaller, this tendency of the tails to become more and more fat is supposed to continue. I mean, all data that we have do not show any saturation as a function of Reynolds. So this is really apparently, I mean, up to the data that we have in the experiments and in the numerics, this is real, this phenomenon is Reynolds independent. So, and larger Reynolds is, and the fatter the tails will become if you go to scales small enough. So I promised to speak also about Lagrangian properties, and just to show you that it's not surprising that this kind of extreme events that you measure in Eulerian domain by looking at the velocity difference fixed on your lab reference frame, you also find again in Lagrangian domain. So for instance, if you follow the evolution of one particle inside your flow, this is a tracer particle inside your flow. So you look, for instance, this is the signal of the velocity seen by the particle advected by the flow. You see that the velocity, the particle experiences some, more or less mild fluctuations along its trajectory, but then from time to time it enters inside one extreme event that is a very small scale tornado, where the particle starts to fluctuate in a randomic but very intense way. And this, if you want to highlight the signal even more, you look at the acceleration and you see that it's really a sort of bimodal signal where you have fluctuations order 1 and sometimes fluctuations order 200 and 300 in these units. Indeed, if you want to be more quantitative, you go back and you measure the PDF of the acceleration of particles advected by the flow, and you see that you see this is the PDF of the acceleration, again, normalized with its root mean square, and you see that, again, the intermittency is slightly different from what you observe in the Eulerian reference frames, because these are different observables, but it's still there. You see fluctuations of the order of 40, 50 standard deviations. These measurements now this comes from a direct numerical simulation, but these measurements now, thanks to the fact that the experimentalists have learned how to measure Lagrangian accelerations in real flows very accurately, we have a perfect matching of one-to-one with the experiments. And just to give you an idea, for those of you that are interested more on theory, I mean, the only way that we have from, let's say, mean field approach, Kolmogorov-like ideas to predict this PDF would predict a PDF like this. So you see that it's, I mean, we are very far from, I mean, the reality is very far from our mean field approximations. You may have you may fail of order of magnitudes to predict the probability to have intense events in a turbulent flow. So this is concerning Lagrangian, and then you can change the density of the particle, and you have slightly different acceleration, but this is another discussion. So this this long introduction is just to convince you, but probably it was not necessarily to this audience, that the flow is very, I mean, the statistics and the phenomenology of the flow is very complex. It is, there are main basic fundamental problems connected to the many degrees of freedom, the roughness of the velocity field, the non-Gaussianity of the PDF, that are really bottlenecks for theory and for numerics and for experiments. And I think it's safe to summarize that we have no way to predict statistics for mean profile or extreme events from the equation of motion. There is no way to predict the kind of PDF that I showed you before from the equation of motion. No one knows how to do it. And also, for those of you that are involved in numerics, I don't need to convince you that there is also no way to perform direct numerical simulation for many realistic problems where the number of degrees of freedom is so large that indeed we don't have computing time enough to perform the direct numerical simulation. But let me also add that even if we would have enough computing time, I'm not convinced that computing is enough to understanding, and therefore, I mean, it's important to develop new tools to ask new questions or better questions for this kind of problems. So my message is that we need quantitative models and tools to model. That is, I mean, we need tools to model because there are too many degrees of freedom, and we need quantitative models to understand the physics of the flow. So our background, just to make a short advertisement of what we do in our group, we come from computational physics mainly, and so we have a huge set of data that span different applications, from traces in inertial particles in turbulent flows, this is emission from a point source, to MHD, or to rotating turbulence, sheared turbulence, not to speak about homogeneous and isotropic turbulence, that is always our test bed for many applications. So the aim of the talk is the following. I will try to touch three different sets of applications. One is goes under the name, I try to summarize here, of data simulations, flow reconstruction, or super resolution. I will be more clear in a few seconds. The second, so this is really, there is no modeling, if you want. It's just trying to understand and trying to extract from the information that you have. Suppose you measure something inside your flow, try to extract as much information as you can, also on what you don't measure. And of course, I mean, in a flow that has very few degrees of freedom, if you measure enough degrees of freedom, you might reconstruct everything. In our case, we have billions of degrees of freedom. So one could imagine that if you want to reconstruct to control exactly the Hooke configuration, you would need billions of measurements. That is indeed the case. But the question is, so if I cannot measure in billions different points of view, points in my system, how can I nevertheless extract information from my partial observability? Then the second question that I will try to discuss is about turbulence modeling, that that also goes under the name of Lagrangian simulation, which might also be connected to predictability. And so I will not speak about predictability in this talk. And in the afternoon, if you are interested and if we have time, I will move more to Lagrangian points of view and discuss optimal navigation and optimal control, optimal navigation on the Lagrangian point of view. So how to steer particles in a preferential way inside the complex flows, and eventually optimal control concerning the controllability of Eulerian structures like Rayleigh-Benard convections, in order to reduce or to enhance the heat transport from one wall to the other wall. And I will mainly focus on applications that are data-driven, so that are in one way or another connected either to machine learning or to reinforcement learning. And I will again always try to have also a connection with some physics-informed or equation-informed baseline. So I will jump a little bit from fully data-driven to physics-informed, and then eventually discuss the very few cases where we can combine the two and to have something that is data-driven but supplemented by some physics knowledge. So let me just discuss the first application concerning data simulation, flow reconstruction, and in painting. I keep one application, but as you understand immediately, this is the domain of applicability is really vast. But the typical problem that I would like to take as an example is the following. You have some complex flow that you want to measure, and there is a cloud or something that obstructs your view, right? So you have partial observability of your flow, or maybe you can measure only one component of the velocity field. There could even be a partial observability concerning the components of your flow, or could be this cloud could be in Fourier space, could be some scales that you cannot resolve, and you want to extract and to know and to reconstruct what you miss. And of course, I mean, if the underlying image is characterized by only 1 degree of freedom, it's enough to measure in one point the flow, and you can reconstruct, right? But unfortunately, we know that the underlying configuration is composed of billions of active and important degrees of freedom. Some are more important, some other are less important. So we played with 3 different tools. 2, I classify them as data-driven. One is all the tool that probably most of you already know, that is just based on what people call principal orthogonal decompositions. So you just try to decompose your flow in eigenfunctions. So suppose that you have some eigenfunctions, and then to fit the optimal coefficients in order to minimize the L2 norm between what you miss and what you reconstruct. So this is a sort of linear optimal reconstruction given the possibility to have, given the knowledge of some eigenfunction that characterize the principal component of your flow. These eigenfunctions just to make things clear, if the flow is periodic, most of the time are simply the Fourier functions. The second tool that is the one where I will put more emphasis is, on the other hand, much more modern. And the idea is that, in some sense, to obtain the reconstruction, the repainting, not in a linear, with a linear orthogonal decomposition, but with a fully nonlinear fit. So where you put in between, when you supply a machine that is characterized by millions of free parameters that you can tune, where you supply the machine with some damaged images, and you ask the machine to produce a fit of what you miss, and you try to minimize the cost, which is just based on the ground truth minus what you reconstruct. So it is, in some sense, the same of a principal orthogonal decomposition, but it's done in a fully nonlinear way with millions of free parameters, not only a subset of coefficients, and in a fully black box way, because the machine is made of billions of connections and nonlinear connections between different layers, and I will be more clear in a few seconds. The third point that I would like to discuss, and even though I will do it very briefly, is on the other hand, exactly the other point of view. So here, data-driven, I need to have thousands, hundred thousands of configurations to train the machine. On the other hand, if I am a physicist and I know that my underlying flow, and I know the equations that have produced the underlying flow, then I can try to use not the data, but the equations. I mean, the equations provide the information that I was searching on the data in the data-driven approach. So one tool that I will discuss briefly is this tool that is called nudging, where you try to reconstruct what you miss just by evolving the full Navier-Stokes equations, and but adding, you evolve the full Navier-Stokes equations on the Ur domain, and you add a linear relaxation term of the flow that you evolve against your knowledge. It's just a penalization against your data. It is a tool used from decades, at least, in the numerical weather forecast community. And the idea is that by evolving the flow everywhere and asking the Navier-Stokes equations to be as close as possible to what you measure, where you have the data, the Navier-Stokes equation will do the job for you. They will reconstruct the flow everywhere. And by staying very close to what you measure, because you put this penalization term where you have the data, and reconstructing something that is close to the attractor, completely physics compliant, where you have the gap. So the question is, which one is the best? How much, please?
What would you put something like, Cindy, or if you want to have to do reduced modeling, but to infer equations? That's not exactly number 3.
No, if you want to infer the equation, you mean you want to infer the parameters in front of your operators. You can do also that by using the same nudging. I will discuss about that. You can do also that by adding terms, right? And then trying to see which parameter allows you to have a better reconstruction. Right? I mean, this, you see, if you are exactly reconstructing your flow, this term is exactly 0. Right? But only if you are using the parameters that are the exact parameters of the underlying fluid. For instance, we play the game, I will tell you later on, we play the game to imagine that these are damaged images from a rotating turbulent flow. And we play the game, what happens if I don't know the exact rotation rate. And I mean, in this way, you can infer the rotation rate by asking that the reconstruction is optimal where you have the data. I will be more clear later on. So just to give you an idea of how these things work when you have the data-driven, the machine learning approach, one can play many different games. One that is very popular in the last few years goes under the name of by using generative adversarial network, or I mean, the computer vision community call them a context encoder. And the idea is that to use a network that is slightly more complicated than what I depicted here, because it's made indeed of two machines that work in an adversarial way, one against the other. Just to give you the idea, you have first a machine that is just a generator. So what you have your damaged images in the input. Then you have a generator that try to first encode and then to decode these. So first try to compress the information, then to explode the information with a neural network, a convolutional neural network in between. And at the end of the day, at the end of this machine, you ask to produce the image that you miss. And this machine is just trained by minimizing the L2 norm between the ground truth. This is a supervised learning. During the training, you need to know what you miss. So you need to use a situation where you have all the information, you remove the gap, and you train the network to reproduce something that where you know what is the ground truth. So this machine is just optimized by refilling the gap with something that is as close as possible in L2 norm against the ground truth. The idea is that once you have optimized, then you show an image that you don't know what is the ground truth, and because it has optimized to reconstruct the attractor, it produces something that you didn't. But if you do like that, it does not work very well. It does not work very well because, you know, I mean, every turbulent people understand immediately the L2 norm is of course very important, but it might be a little bit misleading. Sometimes you can refill, and indeed it happens that if you use also only this network, it refills with the average here. I mean, it could be that the average is indeed, because you have very few information, is the best, is the optimal reconstruction to minimize the L2 norm. But of course, if you refill with the average, it's completely fake. I mean, it's not the correct one. I mean, you are not able, if you only look at the L2 norm, you don't have any control on the PDF of what you produce. And why for a turbulent people, we know that it's not enough to reproduce the peak of the PDF, but we want also to reproduce the tails, right? It is a wild set of events that are not at all of the order of the mean or of the order of the standard deviation. So in order to refill with something that is always physically compliant, you put also in parallel to this machine, another machine that is what people call a discriminator. So it's a machine in some sense that check the PDF of what you produce. So it's a machine that it's trained to discriminate good PDF, bad PDF, good image, bad image, without looking at the L2 norm. It's like when people play this game with faces or animals, they just ask, you know, to discriminate between a cat with the two ears from an image where the ears are top down or things like that. So there are still the ears, but it's completely wrong for the context. And what happens is that, so this machine is trained in this way. You have, it's again supervised. You have a set of images that are true turbulence, and then you have the set of images that are produced by the encoder. And it is trained to discriminate between what is true and what is not true, because you tell. I mean, this is the ground truth, this is the decoder. So, and then you put the two machines in competition. So there is an extra cost. The total cost is the cost of the generator plus the cost or minus the cost of the discriminator. And then what happens is that during the training, this is producing something, and this is trying to discriminate. And then at some point they reach, if it works, they reach an equilibrium where this guy is able to produce something that is good enough to not be discriminated by the discriminator. So it's like if you have an actor and a critic. The actor produces something and the critic tells you that what you produce is not correct. And you know, sometimes miraculously these things work. For instance, I show you here the cost, the total cost of the training starting from a random configuration of the machine. And you see at the beginning, this is the total cost. You start to make it, when you read epochs here, it means tens of thousands of configurations shown. So a training like this, it needed something like 60,000 configurations shown for the training. We didn't reach a good convergence until 30 or 40,000 configurations. So you need really a big amount of data to produce, to train the machine. But then you see that the cost is decreasing, and you see at the beginning of the training, the machine is producing something that is completely fake. And then it starts to learn how to make something that is more or less good. And then at the end, at least apparently by eyes, it looks much better. If you want to see in a movie, these are 6 different trials of regenerating or generating something inside during the training. And so this is during the training. You see that it produces always something that is better and better and closer to the original ground truth. Okay, but then the question is, I mean, again, please.
Can you return then the best norm? Could you like reduce your system to have only one norm at the end?
Okay, so this is a very big question. I mean, it's not clear what is the best norm. I mean, indeed, this is something that I ask myself and I ask many people, but I mean, I don't even know if the question is well posed, in the sense that okay, if you evolve Navier-Stokes, by definition, it evolves on the right attractor, right? Then when you try to reconstruct, you need to, I mean, if you would have L2 norm equal to 0, then you have reconstructed exactly, right? Except maybe a set of measure of 0 or something like that. But I mean, as soon as the norm is not exactly satisfied, the bound is not exactly satisfied, then that norm, I don't know how to reply, because if you prefer to to have the best average, then maybe the L2 norm is the best. If you want to control the tails, you need to put a norm that is highly skewed against strong events.
Tune the norm so that you have less and less discrimination and then optimize the norm.
Okay, yes, yeah, no, sorry, yes, you can do it. I didn't say it, but here there is an hyperparameter lambda that measure the relative weights between the adversarial gain. If lambda is at 0, there is no critic. And indeed, it's important to hyper-tune this parameter, and we do it by hands, trying to the lambda that is the best compromise to have a small L2 norm and a good PDF. But you need to do it indeed. You need to do it. Sure.
So here are you trying to get this? We should regard this as a snapshot of the turbulent at one time.
In this application, yes. In this application, yes. But I mean, the tool is trivially extendable by putting more images at different time as an input and asking to produce, more. Either one, you can use the time either to predict better, showing more images at earlier time, because you imagine that what you have at some time depends a lot on what happened in the past. But you can, in principle, use also to predict in time, but there are better tools to predict in time.
Yeah. Yes, I just don't understand. So you've got the Navier-Stokes equation here.
Yes.
Where does the time derivative of that come in?
In this game, time derivative does not play any role. I will tell you more later on when time derivative might play a role. If you want to exploit time, to take advantage of time, you just need to show in input of the machine more configurations at different time. It's more information, it will help you to reconstruct better. Please.
I mean, if you're trying to start playing a game with the time evolution, could you also add a penalty term and discriminator for the deviation from the
Yeah, exactly. This I will tell later on. Yes. When you have information on time, you might also not always, but you might always also try to put a penalty depending on the evolution of the Navier-Stokes equation. I will tell more later on. So let me speed up a little bit. So then we want to be quantitative, right? I mean, we don't. Images for physicists are not enough. And so I show you a few examples of both statistical and on the other hand, point based tests. So this is just the test on the spectra. This is how good we are able to reconstruct spectral wise the flow, and spectral wise the reconstruction is really great. I mean, it's the black line is the ground truth, and the red squares are the red squares are the ground truth, and the black line is the reconstruction. And just to, as an example, the green squares is the damaged figure. Of course, I mean, if you try to measure the spectra of a figure like that, it's a mess. You have a lot of oscillations and things like that, just to give you an idea of how much you improve. Then another statistical test is about the PDF, because I repeated about the importance of the PDF. In our case, we were measuring the PDF of the, here there are two different PDFs. One is the PDF of the V square, so of the local kinetic energy. And again, the two lines is the ground truth and the reconstruction, which is, these are all normalized with the standard deviation. And then you see, this is the PDF of the vorticity, of the vertical vorticity. The vertical vorticity, of course, is skewed because this is a flow under rotation. And again, you see that this was a relatively mild case where we have fluctuations up to 15 standard deviation. And you see that the machine, which is the dashed line, is able to reproduce the PDF inside the gap up to 14, 13 standard deviation in a pretty good way. So the machine is really able to generate this is a statistical tool. So the machine is really able to generate the statistics of the flow inside in a very accurate way. Then if you look at the PDF of the L2 error, so you ask at every point, how good is your reconstruction? So this is not statistical. This is really point by point test. And then you see that, for instance, even for gaps that are very large, 1/2 of the whole domain, so gaps that are, let's say, that are of this size, right? Size that are affecting many scales in your flow. You have a PDF of the local error. This is percentage-wise. That has a peak of around the 10%. So the typical mean error that you commit is of the order of 10%. And then even in the worst case, where you look at the largest error that you commit with small probability, 1 part every 1,000, you are of the order of 70%. While I mean, if you take randomly a point that has the right statistics, the error would be 200% normalized in this way. So the reconstruction is also point-wise pretty good. If you want to see an example, you see here I show the ground truth, that is the solid line, and the dashed line, that is the reconstructed velocity component along this line. And you see that I mean the nonlinear neural network is able to follow the structure not only visually but also in a quantitative way, in a highly non-trivial way. And you immediately understand here the issue of the roughness. Any linear or analytical interpolator, because the Fourier spectra here is a non-differentiable, would fail. Then last comparison against the GAPI-POD, that is the linear reconstructor, right? And if you play the game with the GAPI-POD, that is the decomposition on a set of eigenmodes, for the 1 square gap, this is the result of the L2 norm of the error for the GAPI-POD, and this is the result for the L2 norm that you obtain with the GAN when you have a 1 square gap. You see that the GAN is always winning up to what is remarkable is that except for when the gap is almost of the same order of the whole image, so you just supply one layer in the framework, the GAN is definitely better. When you have only one layer, so you cannot really exploit some derivative or something like that at the boundary, then in that case the GAN becomes slightly worse, but still better than the GAPI-POD. And on the other hand, when you have random damage, of course, the random damage allows you to interpolate much better. Then the GAPI-POD and the GAN are almost identical, which means in some sense that the linear interpolation when you have random damage is probably the optimal one. Just to another tool that is the one about nudging. Right now we move on the other side. Now we have only equations. We don't have, please.
Maybe before we do that, with those approaches, you're showing that sometimes it works and it works quite well, but there are also instances where you can fool the network, and a minor fluctuation somewhere in the spectrum enables you to, does not enable you to reconstruct even macro or mesoscale features.
Yeah.
So do you have theoretical guidelines to where we don't
No.
know the underlying?
No, I mean,
Yeah,
no, I mean, the issue of robustness and transfer learning in some sense that are connected to what you are asking, to my knowledge, are not completely understood, certainly in our domain. And there are very few attempts to ask. These are key questions. I will say a few words later on, because in some sense, in some cases, the sensitivity of the network to the input information is a good news, because it allows you to do a sort of a feature ranking. That is, you want to understand what is key, for instance, to classify, to reconstruct. So if you see that, for instance, I don't know, that is when you damage one boundary, then the network is completely fooled. It means that the information in the boundary is key. So this is very important in reversal engineering approach to ask questions about the physics of the flow. So in some cases, the sensitivity is a good news. But how to use it in a systematic way, to my knowledge, we tried a little bit. If you want, I can say more. In this case, what we tried, for instance, is to compare reconstruction by supplying different information in the input, either only the horizontal component or also the gradients and things like that, and then to understand how much this improves, to see the sensitivity on the information. But I mean, systematically, I mean, I never saw anybody trying to do that. So just 2 minutes about the equation-informed case, because we all come from the equation, from the PDE world, right? And so what is, for instance, this application is that goes on the name of nudging. As I said, it's on the other hand, it's exactly the opposite point of view. No data, we don't need data. We just need the equations. And of course, then we need the numerical capability to evolve the equations, right? So suppose I know that this equation, this plane comes from a rotating flow, then I can reproduce, then I can try to refill here. And indeed, everywhere in the whole 3D volume, I evolve Navier-Stokes equations in the whole 3D volume, and I just supply a penalization to Navier-Stokes that if the velocity here, where I don't have the data, sorry, here, where I have the data, is different from what I measure in the framework, then the Navier-Stokes corrects the evolution. And so this is the really simply mean for those of you that know about penalization when you want to put walls on a Fourier spectral code, is exactly the same. The problem is that the penalization is against the data that is not a wall, but it's your measurements, right? What is the and you can play this game and then you compare with the generative adversarial network. We are starting to do that. We didn't still have a systematic way. Preliminary results tell us that it's more or less of the same order. Before saying who is better, one should do it in a much more systematic way. What is again the big difference? In one case, okay, this was the preliminary results of the nudging. Right? So this is it's interesting that you can even you supply one image at one time, and then the Navier-Stokes is going to go around it, right? Producing fluctuations when you refill, but still, I mean, around where you have the data, Navier-Stokes try to synchronize with the data that you give. And the kind of error you see is of the order of 10%, but this is a really preliminary result, which is of the order of what we observed for the generative adversarial guy. Then, please.
How do you adjust your N?
This is again an hyperparameter. It's an hyperparameter because this is the intensity of the nudging, right? So it's an hyperparameter because you don't want to be extremely stiff. I mean, you don't want to impose exactly one configuration outside. So it's we adjust it again by hand. I mean, you can have a first order estimate because this is the inverse of time. So you want to adjust it more or less with the typical time scale of the fastest scale that you have in the turbulent. But at the end, I mean, frankly speaking, we adjust it by hand.
Have you tried several values or?
Yeah, we're trying several values. I mean, and seeing, just checking which is the one that gives us the best reconstruction inside.
So it's not just a matter of time scales which needed to reach the final state or the best.
No, the transient initial time is not very important because, for instance, we started from 0. And of course, the system is forced. This is a forcing term, right? The system is forced in order to produce the right configuration outside, and then starts to oscillate inside. The optimal N to have the best reconstruction, we fine tune by hands. Please.
And if you are in high results, it doesn't become too difficult. I mean, you have to wait for the scale to be reached.
Absolutely, absolutely. I mean, in this paper, I know, maybe it's not here. Sorry. Yeah, in this paper, for those of you that are interested in this paper, of 1 year ago, we did a systematic study of nudging only. So of how much information we need to supply to reconstruct better and better, and dependency on Reynolds and everything. Yeah. I mean, it's not surprising, for instance, that if you want a whole reconstruction, you need to supply information that is almost as dense as the Kolmogorov scale in your flow. I mean, that's. Yeah, I mean, yeah, that's that's a good remark. Please.
Do you have a sense of to what extent the success of these approaches depends on the fact that we use a rotating system that with large features exist? I mean, if you just had, non-rotating.
Yeah. Okay. Yeah. For nudging, yes. Nudging does not know about large-scale feature because it has the Navier-Stokes equations that have the right physics, whatever it is, right? So nudging is pretty robust because you supply a lot of information. You supply the equations. For the data-driven things, again, the fact that you have large-scale features like the big vortex, it might be important, for instance, for the L2 norm, because there is where kinetic energy is concentrated. But when you check the PDF and the tails and so on and so forth, the big scales are not important. And indeed, we applied the reconstruction even for cases where rotation is not strong enough, so you don't have the big vortices, and it's working decently, I would say.
Have there been studies of nudging that contrast the cases where the, shall we say, the known region drives the unknown region, and with the case where the unknown region
Sure. So people in the numerical weather forecast community did a lot. So they have this multi-scale problem like Lorentz 96, where they have different scales. So you're supposed to have the driving, the slaved scales. And of course, when the unknowns are the driving scale is much more difficult, right? Yeah. So it's this has been studied. In our case, in some sense, it's a little bit mixed because it is we remove a piece in configuration space, so there is everything there, driving and slaved. And in this paper, we do it nudging also in Fourier space, where indeed we changed the nudging windows either on the large energy containing scales or on the small scales. And of course, I mean, you expect what I say, that it works much better when you remove the slaved ones. That's.
In this one, you're nudging it towards the snapshot again.
Is one snapshot in time? Yes.
And you'll get there. But now you nudge it in time.
Now I'm nudging in time. So I have one.
Is it clear that your state nudging it towards a snapshot will be the same as the snapshot state, which is really just on its way through heading somewhere else?
No, ask again, sorry.
When you take that snapshot,
yes,
at the next time it will look completely different, right? It's on its way evolving.
Sure.
Is it? Do you guarantee that by nudging it towards this steady snapshot,
yes,
that will reproduce the flow? It's not clear to me that it will reproduce the snapshot.
No. I mean, okay. I will certainly help Navier-Stokes because of this penalization term to stay in time as close as possible to this data. But of course, Navier-Stokes evolve everywhere. Yeah. And so, I mean, it is not exactly the same. Indeed, if you see here, this is again, the velocity along this profile. You see that both the original and the nudged they have a mismatch even where you supply the data, because Navier-Stokes is evolving everywhere. So it's fluctuating around your input where you have the input and providing a best guess that is compliant with that constraint according to Navier-Stokes equations. So, I mean, if I would have also other snapshots at the different times, then I can apply nudging, and indeed in this paper is done in this way. I can apply nudging also in time. So this quantity changes in time. Of course, it will be better. Of course, it will be better. But our question here was, suppose I have only this information, how much I can use Navier-Stokes equations to reconstruct? So last point that I wanted to touch is the mixing between physics informed and data driven. Right now, because at the moment we have seen either something that is completely blind. So here there are no equations. The machine does not know anything about the physics, to something that is on the other end completely physics compliant because it's fully aware of the equation of motions. Of course, you know, in this first case, right, you need hundreds of thousands of configuration to train. Then once you have trained and you show a new image, the result is instantaneous. I mean, it takes 1 picosecond, right? On the other end, here, you don't need any data for training, only the measurements, only one measurements. But to refill with the equations, you need to do a three-dimensional numerical simulation, maybe at high Reynolds and with all the difficulties that takes millions of CPU hours and so on and so forth. So it's really the two approaches are completely distinguished. There is recently, in the last couple of years, people have tried to combine the two. How they do it? They do it as you already, somehow with your questions, you have already imagined. That is, suppose that you have now measurements, sparse measurements, but both in space and in time. For instance, this is it's exactly the measurements on the Lagrangian trajectories, for instance, right, that I show you at the beginning. You have anemometers that go around in your flow, and you can collect measurements in space and in time. So this is, for instance, an example where they collect measurements downwind of a cylinder in 2D. So the problem is very, very simple. Where they're supposed to have particles that evolve, and then they collect the concentration of the temperature, let's say, or the concentration of a dye, where they are, and the position, the time where they have made the measurements. So you have information about the concentration at different points and different time. Now, if you have information at different points, different times, you can try to refill with a network in a linear way, but using also the constraint of the equation of motion. Because, for instance, you can train a network by putting in input time and the position where you have the measurements, and you ask the network to predict all what you need for the equation of motions. What do you need for the equation of motion? You need the concentration, and then you need the two components of the velocity field and the pressure. But this is not enough. You also need the derivatives of these fields with respect to the position and to time. But because these are going to be nonlinear function of t, x, and y, you can back differentiates to the network. These have an explicit expression, even though made of 1 million of free parameter. You can back differentiates and therefore also estimate not only from the network the value of u, v, p, and c, but also the value of the derivatives. And then you train the network by combining a cost, doing what? First, you want to minimize the L2 norm with respect to the measurements, because you have the concentration where you are. So this is your ground truth, right? The measurements of the concentration, and this is the output of the network. So you want, first of all, to reproduce the concentration where you are. And then you also put an extra cost, which is the error that you make in reproducing the equations. You see, if your derivatives would be exact, then, because you know that they satisfy this equation, you would have this E2 equals 0 for the component U. This E3 equals 0 for the component B, E4 is equal 0 if it is divergence, and so on and so forth. So you have not only an L2 norm that reconstructs your data as I had here, right? As I have here. But I also have an L2 norm that tells me how much my reconstruction and the derivatives of my reconstruction are far from the equation of motion. Of course, these are very, very delicate hyperfitting because, again, you need now, I go back to one of my first slides, you needed to extract derivatives most of the time on situations where the flow is highly rough. And indeed, I mean, up to my knowledge, up to now, we have success of this kind of approach only in extremely simplified cases like a two-dimensional flow that is completely smooth and where Reynolds number is very low and so on and so forth. But I mean, the idea is new. How much it's applicable, it's still, from my point of view, not clear. Okay, this I already said. I think it's already 1 hour. Huh? This I already said. It was just my summary about the data-driven. Let me just summarize again. It's thousands of configurations to be trained. It's no physics compliant. And once trained, the refilling is sometimes. These no physics compliance can be partially solved by adding this constraint on the equation of motions. But again, to add the constraints on the equation of motions, you need to have data that depends on time, such as you want to extract also the temporal evolution. Right? Notice that maybe it would be nice to stress that the tool is very general because one could say, okay, but I mean, we don't know the forcing. We don't know the boundary condition, right? I mean, it's not only, most of the time, maybe the boundary condition is very complicated or the forcing is unknown, right? In the atmosphere, the forcing is unknown. But still, an approach like that, you can ask the network also to produce a guess for the forcing. For instance, I mean, it's another function. Of course, it will become more and more difficult. Or you can impose the boundary condition because these are known situations in your flow. So you can, as if you have measurements where you have the boundary conditions, and therefore you can impose in your cost that the fields that are produced, you penalize the cost if they are far from the boundary condition. So the tool is indeed in principle, very flexible. Then how it can be applied, it's in real situation, it's still unclear. The other approach, the equation-based, as I said, you don't need training because both Navier-Stokes did the job for us. And it's, of course, fully physics compliant. But I mean, of course, the minus is that you need heavy computational needs. But let me also remark that also nudging can be used if you don't know exactly the equation of motion. Because you can do the game that you were mentioning before. Suppose I don't know exactly the intensity of the diffusivity, right? I can nudge and I can repeat the simulation with different diffusivity values. And the one that will give me the best reconstruction, where I know the data, it is a way to infer the equation of motions. Of course, it's much more demanding numerically because you need to repeat the three-dimensional simulation. If I have 10 minutes more, I will say something about this point, the physics inferring. So something that is strongly, I mean, somehow connected, but not exactly the same problem before. So suppose now, let's change the question. The question is, you have different turbulent configurations, and you don't know how to classify them. You know that they come from maybe different Reynolds number, different Rossby number, different Rayleigh number, different magnetic Reynolds number, but you don't know because the situation is evolving in time, and you need to classify. You need to infer the physics. And you want to do it in some optimal way. So the game that we played is again using this rotating turbulence because it's a way to, we have a clear free parameter, the rotation rate, that by changing the rotation rate, you can change from a situation where you do not form the big vortex structures to a situation where the two-dimensional columns becomes more and more coherent. So you have a clear free parameter that you can play with by keeping fixed the Reynolds, almost so keeping fixed the dimension of the box. So it's easy also to do it from numerical point. So the question here is, suppose I need to plan a glider that must navigate in a flow, right? And this glider, I know the policy to plan the glider depending on the intensity of the typical columnar updrafts, right? But this, I mean, I don't know exactly in which region I'm going to fly, and so I need a rough estimate of the degree of turbulence that I'm going to meet. So I need to have a classifier that tells me, look, you are in a quiescent region, you are in a region where the vorticity is very coherent and things like that. So this is somehow the background idea. And as you see, when you change the parameter, just to give you, okay, the spectra, you have a big difference in the spectra only when you move from year to year, because you deplete the large scales. If you look at the total energy, well, if you can measure for many time, you can easily classify. But if you have one snapshot, this is the total kinetic energy. If you have one snapshot, could be any point in this time evolution. So it would be impossible to distinguish what is the omega. Even if you have more measurements, for instance, this is the PDF, the joint PDF of the moments of order 8 and the moments of order 4. Suppose you look at the extremes of your configuration, you see that the joint PDF, they superpose, unless you have a situation where omega is small, all the others, omega, the PDF superpose a lot. So if you have only one instance, you will never, they do not cluster. You will never be able to say if you are in this, if you have an instance here, you cannot say if you are omega 30, 5, 20, because they are on the same, more or less on the same area. So how can you classify from one snapshot only? Well, you can use nudging, for instance. This is what I was saying before. Suppose you have one snapshot, then what you do, you nudge, you pay a lot of computation, you change omega, you scan all possible omega, and if omega is much, and then you look at the error that you commit in reconstructing where you have the data. For instance, I don't know, suppose you have a gap here. Then you measure the error that you commit in reconstructing where you don't have the gap as a function of omega. And then you see that when the error goes to a minimum, well, this is probably your best guess for omega. Here we do it. We did it in this paper by changing the large scale shear and the omega rate. And I mean, it was in all cases, even so, either changing omega or changing the large scale shear, he was able to scan to find a clear minimum by to identify what is your optimal parameter. Of course, this is very demanding. It means for each one of these omega, a full three-dimensional numerical simulation. Then we tried also with a classifier, so with a machine, a black box, please.
I don't think you have said it, but it shows, as you expect, strong sensitivities to the observable to which you nudge, towards which you nudge.
Yes.
Do they correspond to what you would expect physically? The difficulty in reconstructing, or because you know that, for instance, in some cases it's going to be the Rossi parameter that's the key part, or the Reynolds parameter the key part. If you're informed by that physics, does it help the reconstruction or no?
Okay, so people start to ask this kind of question. This is again what we were discussing before, a sort of a Fisher ranking, right? Understanding what is, for instance, I mean, if I want to reconstruct at a large scale, right? Probably if I change the viscosity a little bit, it does not change anything, because we know that the large scales are more or less Reynolds independent, right? So indeed, one can play this game and saying and asking what is the key parameter that is counting more. In our case, I mean, it was somehow by definition, we knew that I mean the key we kept the forcing fixed, the right one. Right, so we knew that the main parameter was omega. I mean, that's it was just a sort of a priori guess that this was the key parameter. But in principle, you can do what you do. You can do what you say. So on the other hand, the other approach is data-driven, is to using again a network. In this case, it's a simply classifier. So it's just a nonlinear regression that tells us, again, fully supervised. So we train with hundreds of thousands of different configurations with a different omega, and we inform the network what is the right omega, and we minimize the cost with respect to the output of the network. The network gives us in output one number, one real number, and if the number is very far from what we know during the training it should be, we penalize the cost and we make a back propagation and we optimize the training. And again, you see that during the training is improving the loss, the cost is diminishing. And if you look at the PDF of the guess with respect to the real one, you see that at the beginning of the training, the network is almost blind, is predicting something that might be completely wrong. And then by increasing the training, this is the PDF of the last epochs, the network starts to be strongly peaked around the ground truth, which is, because this is normalized, it's around 1. So indeed, the training converges. And then here, what we did, we compared again against other tools, not, let's say, machine learning inspired. So for instance, we compared again against Bayesian inference. So what is Bayesian inference? You simply, from your set of data, you can start to extract empirical joint probability between the rotation rate and some observable. So for instance, the PDF of here I show you the joint PDF of the gradients. I think this is the gradient square. There is but anyway, it's not important. The gradients and of the kinetic energy, and you see that again. If you look simply at the joint PDF, it's very difficult to cluster, right? There are some omega that are clusterized, some omega that are clusterized, but between the two, they are completely overlapped. Some other omega are completely overlapping one with the other. So we already see that by using Bayesian inference, it will be very difficult to classify. This is the result. So this is, for instance, the comparison between the network classificator on the left. Here you have on the y-axis you have the omega that you have the output of the network, and on the right axis, on the x-axis, you have the ground truth. And you see that the network is for many different omega is able to classify in average very well with some spreading. For very large omega, the spreading is larger, but the correlation between the prediction and the ground truth is very good. If you look at the Bayesian inference by using only V-square, it's a disaster. So if you have only the input on the V-square from your images, that is the only things that we provide to the, in the image we give V-square, then it's you see, it's the correlation is almost at 0. There is, here for this set of omega, the Bayesian inference is not able to distinguish. They predict with the same probability many different omega. If you start to improve, for instance, and you provide the Bayesian inference with the gradients, correlation starts to improve, and you have even though you have a larger scatter, if you do Bayesian inference by providing V-square and the gradients, then the results starts to be closer to the network, even though the scatter becomes larger. Of course, one should play this role by continuing adding information. More observable you add, more statistics you need, because you have a joint PDF conditioned on 3, 4, 5, 6 observables. So if you have a finite set of data, at some point there will be a trade-off, right? So this cannot improve forever if you have a finite set of data. Just to give you a quantitative idea of the two methods, here we estimated the error of the network against the Bayesian inference in order to, by fixing one omega and seeing what is the typical error by predicting in output the right omega. And again, you see that the neural network gives you a deepest minimum than the Bayesian inference, which is, in some sense, a signature that you are a little bit more performant. 2 minutes to answer another question that you posed about the feature ranking. And then I just advertise for the next talk in the afternoon. What you can play also with this network, you can play this game. For instance, for the classificator, you can start to remove parts of your data. This is what people in the computer vision community call occlusion. So you see how much the network is able to classify after being trained. You trained, you freeze, and then you see how much the classification becomes worse by starting to occlude some parts. In the computer vision, they do it often to understand if to recognize a cat from a dog is better to have the image of the mustache or of the eyes or the tail, right? And so they understand what are the features, the key features in the classificator. Here is more difficult because we always have these big vortices, right? So we started to apply this occlusion by removing tile by tile and measuring how much it becomes, how much that tile is relevant or not. So if the classificator becomes better, we say it's not relevant. If the classificator becomes worse, we say it's relevant because we have removed something that is key to classify. And you can play this game. For instance, here for one image, you see that the blue scale is, in terms of this indicator, the blue scale is relevant for the prediction, right? And the red confused the NN prediction. What does it mean? It means that you see that the red it's on the shear region, right, of our image. And you can start to ask questions like this, and then to try to understand if there is a correlation between what you classify red with some aspects of the physics. This is the best that we try to do in order to, in some sense, open the box and see what the box is indeed using to classify the system. And then you see that when you use this classification and you remove things that are confusing, indeed and you look at the joint PDF of the remaining, indeed you start to cluster. So indeed this is you understand what the network did, right? It's giving more weight to those regions that allows you from the joint PDF to have something that is more separated, and therefore it's easy to cluster. Okay, then let me advertise what we can discuss in the afternoon. In the afternoon, I think more than discussing about large eddy simulation, but I mean, I would be happy to answer questions and curiosity about large eddy simulation, even though we don't have a very good experience, high experience for the machine learning approach. Maybe in the afternoon, I would probably, if you are interested, to discuss the two problems concerning Lagrangian, concerning reinforcement learning. So, which is a different way to optimize something where also time enters into the game. So the system needs to be optimized. You need to optimize a cost function, which not only depends on time, but depends only on the actions that you do. So it's a two-way interactions between the guy that optimizes and the environment. And if you want, I can summarize briefly one attempt that we did to perform optimal steering in turbulent flows. So to move one vessel from one point to another point with a flow that is evolving in a chaotic way, and allowing the vessel to be advected, of course, by the flow, plus a control. And the control is just a velocity intensity plus a direction. So the vessel it has the engine steering always at the same intensity, and you can only change the direction in among a few preferred predefined directions. Of course, if the steering velocity is at 0, the problem is impossible because the vessel goes where the wind brings it. If the velocity is very large, the problem is trivial. You just go straight from A to B. If the velocity is not 0 and smaller than the typical intensity, the problem is non-trivial because you want to take advantage of the flow to reach in the shortest possible time the position, and at the same time doing it in optimal. This is the problem that is very old, goes under the name of Zermelo, goes back to the early, the 20s of the 30s, indeed, of the last century. And then the other point that I can discuss in the afternoon is optimal control based on a Eulerian system of heat transport. So the question that we ask ourselves is, typically you have a Rayleigh-Benard cell. So it's heated from below, cooled from above. So it is naturally unstable. And you have a heat that is transferred from the bottom to the top wall. And you want to change the boundary condition here, the heating, in a way that you optimize something. For instance, the heat transport, either by decreasing the heat transport or increasing the heat transport by keeping fixed, for instance, the mean temperature. So you want to move from a homogeneous heating to some non-homogeneous heating and cooling, keeping fixed the mean temperature, but controlling how much the flow is transferring it. And this we did it by, again, by reinforcement learning, by imaging that we can measure inside the flow something, and then inventing or asking a neural network to give us the right policy, depending on what I measure in the bulk, what I needed to do on the boundaries to control the transfer. This, of course, is a problem that can be transferred to many other situations where you want to control the flow from the boundary. Okay? And which is also, in some sense, philosophically connected to the problem of data assimilation, because there is also the key issue of where do I need to put the probe to better control, right? Because, for instance, in a flow like this, maybe if I put the probes close to the boundary, is better because the flow is boundary driven. Right? So not only I needed to find an optimal policy to control, but the optimal policy, of course, depends on what I can measure. So if I understood given a certain amount of anemometers that I can put in my flow, if I understood where to put them optimally to reconstruct the flow, probably is also the way to use that configuration as input for the control problem. Even though, I mean, I say probably because we never tried, and I don't think anybody has ever tried. So let me conclude, for those of you that are not here in the afternoon, saying that we are setting up in our group in Rome, thanks to the funding from the European Commission, an open database to host data from other groups too, to set up challenges, benchmarks for the community. So we are very keen to host a set of data from other groups that could be made open access. And the database is not only passive, so it's not only a storage, it's a database that has a well-developed interface where you can search the data, standardize, add the meta tags, and also develop Python interface tools to analyze the data on site. Because as you know, I mean, whenever you have 1 terabyte of data for a big database, I mean, you don't want to download them on your local resources to make the analysis. So the idea is to have here a big interface for the community where we can set up data high quality, high quantity. That is the first step to advance in this kind of data-driven approaches. I think I stop here and I thank you for the attention.
Thank you very much. Well, Carlos.
Yes, thank you for this very inspiring talk. Because turbulence is a multi-scale physics problem. There is a dream, at least in the physics community, to develop active feedback experiments to act on a specific scale and to see how other scales are modified. This still is a dream under discussion by experimentalists, including myself. So I wonder whether you have any thought about this possibility in your personal work.
Okay, yes, thank you for the question. From a numerical point of view, it's much easier because you can easily cook, let's say, artificial forcing schemes that go and touch only some aspects of turbulence, right? And people played with that since almost ever. We also played recently by, for instance, removing only degrees of freedom in a fractal set in Fourier space, or removing only some helical degrees of freedom. So numerically, it's much easier. Experimentally, and you can play, and this is a sort of, let's say, systematic future ranking. I remove those degrees of freedom and I see what is the action. Or I force only on those degrees of freedom and I see what is the action. Experimentally, the only way I see one can act on the flow in an active way is by using particles. So by having maybe smart particles, or maybe not extremely smart, but particles that are, that by definition, they go and preferentially weights only some degrees of freedom. For instance, an example that everybody understands, bubbles, right? If you put bubbles in your flow, they are, because of centripetal force, concentrated on high vorticity regions, right? And so this is a way to have a passive tracking of high vorticity, but suppose you are an experimentalist smart enough to actively modify these bubbles from external tools. I don't know, making them collapsing or oscillating. It's a way to force, right, or to going and then in a surgical way to interact with the flow. This is, I mean, for instance, numerically we played with that game because for us numerically is easy. I have my bubble, and where the bubble is, I force, for instance, or I dissipate. But then translating this numerical tool to a real experiment, I mean, it's your job. But I think it's really the key question. I mean, we will not advance if we don't have a way to actively pose a question to the flow. I fully agree.
Another dream is to produce surrogate models for turbulent transport coefficient, like turbulent viscosity,
yes,
or the turbulent diffusion coefficient for tracer. Try that.
Okay, this is what I say that. Yeah, I mean, a lot of people have started to try by using data. I mean, of course, by using this was my slide about large eddy simulation, right? That is, you have a closure, so you evolve only the flow on the large scale. So you want to guess what is the small scale transport, right? And I mean, of course, we know there are hundreds or maybe thousands of physics-informed models, right? Smagorinsky, dynamic Smagorinsky, whatever. I mean, there are Lagrangian evolving small-scale closure. There are many. People have started to play it with this data-driven approach. So saying, I supply my large-scale flow, and I ask 1 million degrees of freedom fitting, or maybe 10 millions, or maybe 100 million degrees of freedom neural network to provide the closure. And I have mixed feeling. We started to play. We started to play since very recently on these things, and we have results that are not convincing at all, quantitatively speaking. The results that exist in the literature are very qualitative. If you want, we can discuss more. There is also here one idea that is very promising, that is not trying to do this, which is, you see, a sort of a priori guess. You have instantaneous large-scale configuration, and you predict your closure. There is no information on the time evolution, not at all. So there is one very promising scheme that goes under the name of these PDE solvers in the loop. People from the machine learning community, in particular the Google team and also other teams, also in France here from Telecom Paris, have started to play the game, which is highly non-trivial, to put the solver, the Navier-Stokes, in the machine. So you have as input the velocity field at the large scale, sometime, and as an output, you want the velocity field at a much later time. Not too late because there is the Lyapunov exponent, but I mean, after 10, 15, 20 time steps. So you do not optimize the instantaneous attractor, but you optimize also the tangent space because you need to control also the evolution. This is much more complicated because you need to take your field to evolve, to have a guess for your subgrid model, to put the Sacred model, to evolve the Navier-Stokes, to take it at time t+1, to put back on the network, and then minimizing only after a time delay. But this is really is a physics informed, because it's an equation informed evolution. This, I think, is very promising. At the moment, has been applied only to 2D turbulence flow decaying with spectra k to -5, so to almost a very, very small dynamical system with a very, very small attractor. So the feasibility to larger and realistic cases, to my knowledge, is not proved.
Can you speak a little bit about the ability for the neural networks to use like transfer learning or like
Yeah, okay, that's a good.
Specific example, like you showed this example of protein.
That's a good question. That's a good question. Transferability is a very important. Transfer knowledge is a very important issue, of course. So the networks do not generalize very, very poorly. Just to give you an example, this was the classificator, right? And we trained from omega, from this minimum value was 2 up to 30, I think something like that. If you show an omega 40, it is almost completely random. It does not extend outside the convex hull of what you have shown. I mean, that's it's very difficult. I mean, at least to our knowledge, it was impossible for many reasons. First, because there is a problem in transferability. Second, because most of this network, when you train, now is the non-expert that is speaking, right? Because we are not experts of machine learning. So maybe people from Google team or DeepMind, they do better. But typically these networks, when you train, they need a normalized input. So you need to, you cannot train with the data that are very different in the training set. So, I mean, as soon as you go outside your windows, you don't even know how to normalize it. I mean, it's in the input. So I mean, we have not been able to really transfer knowledge in a strong sense. What we do is to transfer knowledge in a weak sense. What does it mean? It means that, for instance, suppose you want to refill, right, data for one given set of 1 omega, right? When you want to train the network for a different omega, you start from the network that you have trained earlier. So this transfer of knowledge is always done, and it helps a lot. But you cannot really go beyond. I mean, at least we have never succeeded to be able to extrapolate.
In the first part, while you learn the V, can you also maybe check with the Lagrangian part, like how good you do? Like, say like reconstructed images or with nudging or something.
Yes.
And then you measure the accuracy on the Lagrangian. A bit like what you want.
Well, in yeah, yes, yeah. Well, in principle, you can do it, but if you want to be fair to reconstruct the Lagrangian evolution, you need also the snapshots at different times because the particle evolves, and in the meanwhile, the underlying flow is. Yeah, we didn't try, but you can do it. We didn't try, but you can do it. Yeah, it's a good idea.
How well do these games work in systems where the flow, say, undergoes or passes through a phase transition in the course of the evolution? Can you, for example, predict the passage through the phase transition?
Yeah, that's a good question. I mean, you need to. I didn't speak at all about that problem because you need a different approach. So you need networks that are able to predict the evolution. Right. That are these are typically time-dependent neurons that have this time delay and that are able to take advantage of the Markovianity or no Markovianity of your model. And there are, I never played with that, but I saw recent attempts to predict, for instance, relaminarization. You know that, for instance, in turbulent pipe flows, for a huge range of Reynolds, there are paths of turbulence, and then they decay, they die with a time that is exponentially distributed. And so people have tried to use this kind of time-dependent networks, training only on the windows where the flow is turbulent, and predicting the time of relaminarization. And they claim statistically, pretty good knowledge. Then there are other attempts that goes under the name of reservoir computing, which is a slightly different approach because it's a network that is fully frozen concerning the connections between the neurons, and you only optimize the last layer. It is the layer that brings you from the black box to the output. And these are networks, developed recently by the group of Ed Ott at Maryland, for instance, but many other groups also, that are particularly suitable to predict the time evolutions, because you have x at time t, and the network gives you x at time t plus delta t. You can use it in open loop, just predicting the future, or in closed loop to predict the statistics. And also these networks have been recently used to predict transitions in always small dimensional chaotic systems, right? Transition from one part of the attractor to another attractor and things like that. So in principle, they can be used. They have been used also recently, but I didn't follow very closely, to predict an inversion of the magnetic field in the dynamics of the Earth, right? Because there you have these big jumps in the magnetic evolution. So in principle, these are again strongly nonlinear, order of millions free parameters to predict, to learn the structure of the dynamics. That's in some cases where the underlying dynamics is very simple, the network learns exactly, because imagine to have a Lorentz system with 3 degrees of freedom. You just need to learn x dot, y dot, z dot. If you have enough degrees of freedom, you exactly fit the nonlinear term, and therefore you exactly learn the evolution of the. Of course, you never beat the Lyapunov exponent. You cannot beat the Lyapunov exponent. Then, if you make even if you have the exact evolution, but you make an error at the beginning, that's the error propagates.
Okay, last one, maybe Biferale.
Yeah, regarding the bifurcation, so to follow up on Pat's question, could you say, if you have a situation where you have a previous state that is very well known, and state after the bifurcation that is measured fairly well known, could you do a combination of forward modeling of the pre-transition state and then reverse time modeling of the bifurcated state?
Reverse,
how they essentially interpret.
What do you mean reverse time modeling? I don't understand.
No, if you do forward modeling,
yes,
you have a state that is very well known analytically or
yes,
for measurement. You let the system go towards the bifurcation, but then if the state afterwards is very well known.
yes.
To just get to the actual bifurcation dynamics, you do the reverse.
That's a good question. I never saw it. This kind, for instance, this reservoir computing, they work in one direction only. I never saw attempts to maybe apply another reservoir computing on the reversal dynamics and asking to match something. I never. It's a good question, but
It's in principle mathematically doable.
Yeah, of course. Yeah, of course. Yes. It's a boundary condition problem in time. Yes. Frankly, it's a good question. Frankly, I never saw it.
Sometimes I get problems of overfitting data.
Yeah.
So how big do you need your machine learning to be when you have
Okay.
efficient data?
Yeah, this is another very good question that it's the answer is I don't know, and nobody knows. And if you ask this question to all practitioners, they will reply, you need to try. And that's really for our community, this is a key question, right? because if I wanted to perform a numerical simulation of a turbulent flow at Reynolds 1500, I already know a priori what is the computational power that I need. I can estimate more or less, right? The time step, the time resolution, and so on and so forth. With this machine, you don't know. I mean, it's very difficult. This is what I say here, you know, need for physical dimensionalization, network structure versus physical parameters, deepness, structure, coding and training data versus Reynolds, Rayleigh, time to solution, mass fraction. Nobody knows. And this is really, I mean, for physicists, this is the main point, because I mean, if until when we are not going to have such kind of vocabulary, saying what is the frontier, what you can do, given your resources, how much you need, it's shooting in the dark. That's a big. But this is, you know, I mean, we are in a sort of inflation, right? I mean, everybody is ourselves in premise is trying to apply to something that looks interesting, but this, I mean, we really needed to stop. I think that's the aim of the database. The aim of the database is to put challenges. You see, okay, we have this data. Let's different Reynolds. Let's understand what you need to achieve some degree of accuracy. But that's a key question.
Okay, let's stop here. If I understand correctly, this afternoon we'll have a small twist. Luca's lecture is not going to be open to students only, but to everyone, because for what I understand, it's better designed that way. Okay. So thank you very much.
You're welcome.
So we reconvene at